Hi, physics students. Sorry I couldn't be there to give you this lesson, but I want to make sure we don't fall behind. This is your warm-up for today, which hopefully you've already done. If you haven't, go ahead and pause the video and work through this on your warm-up paper, and I will stamp it and we will go over it next class. Feel free to work with your partners to get some help, and then we will jump right into LR circuits, which are inductor resistor circuits. So like our previous circuits unit, Kirchhoff's loop rule and junction rule both apply. The junction rule is the same, and the inductor, Kirchhoff's loop rule for inductors is new. So I'm going to go over how to do Kirchhoff's loop rule for inductors. In this scenario, I want you to notice we have both the loop and the current going in the same direction. Yes, it is possible for them to go opposite directions, but I want you to try to avoid that at all costs for inductors because it causes you to have to memorize more equations and scenarios. And so prioritize loop and current in the same direction for inductors. And then if that causes the current to go the opposite direction of your loop in a resistor, then at least you know how to do that pretty easily. Okay, so there are two scenarios for inductors. One is that the current can either increase or the current can decrease. If the current stays the same, then the inductor doesn't do anything. In this first scenario, if the current is increasing, and this is the current through some sort of power source, then you have a induced current that opposes it. Now, the expression we use for voltage is negative L di dt. Now, I know this shows it as a positive voltage, but we can get the positive and the negative just based on this initial equation that's in your equation sheet, because if di dt is the change in current and current is increasing, that means di dt is positive. If it's positive, this negative sign means that it's going to be the opposite direction of your original current. In the second scenario where this current is decreasing, then we've got a induced current that opposes the decrease. And so a decreasing current means a negative di dt. Well, this negative di dt cancels out with the negative in front, and so you have a positive L di dt, which I know they call it negative voltage, but it just means you are getting a positive value in your equation, which then goes in the same direction as the current in your circuit. So in this scenario, I'm going to have you pause the video, read through the directions, and try to come up with the equation for Kirchhoff's loop rule. I want you to note that they are telling you to evaluate the loop in the counterclockwise direction, and that's just so that your signs aren't complete opposites of what they have in the answer key. So pause the video and continue when you're ready to work through the answer. All right, hopefully you guys were able to get this, but I'm going to go through it step by step. Current goes out of the positive and into the negative. And they said loop should go counterclockwise. So my loop is going in the same direction as my current. And it is going in the same direction through my inductor, which is my priority. All right, so first thing we have to look at is, I like to start at the battery. We're going out of the positive side. That means that I am gaining voltage from my battery. That eliminates C and D. As I go through my inductor, one thing I forgot to mention is that my resistance is increasing. What does that mean about my current? Well, based on Ohm's law, as long as my voltage is constant, increasing resistance means decreasing current. My inductor doesn't like that, and so it's going to induce its own current. This is induced current in the same direction. That means I have a positive L di dt. Now, in these scenarios, they're both negative, so I don't even have to finish the problem to know that A is my answer. But it's always good practice, just in case you overlooked something, to make sure that my current and my loop are both going to the right. That means I have a voltage drop through my resistor. Here, it's a negative IR, and this is my answer. Okay, so in this next slide, I didn't mean to put that there, but we were going to analyze what is happening to the current, the voltage through the resistor, and the voltage through the inductor. Is it going to be an exponential decay, or is it going to be an exponential approach? Well, what we know is that once this switch is closed, the inductor is not going to like the fact that the current is going from 0 to some maximum current over a very short period of time. So it is going to oppose that. By opposing that, it means it's going to start this EMF or this current from this EMF off at 0. And then over time, as the resistor is opposing that change, the changes in current is decreasing, which means that the inductor is providing less and less current and less voltage until it's no longer providing a voltage at all because the current is no longer changing. The change in current decreases over time, and therefore we've got maximum current going through the battery and going through the circuit as a whole, and it's all coming from the battery. The second scenario, so here's my current here. The second scenario I already answered for you, but V equals IR. If we know that I does this, and the voltage through the resistor the resistance is constant, then if the current is 0, the voltage is 0, and as the current maximizes, the voltage maximizes. And then last but not least, the voltage through the inductor is how much is proportional to how much current it is inducing. So in the initial switch at time equals 0, the inductor is inducing maximum current and maximum voltage to oppose the current that's being pushed out by the battery right away. And so it starts off maximum, and then again, as the change in current decreases, the inductor works less and less. The induced current is smaller and smaller until there is no change at all. And so the inductor then has 0 voltage. So one thing I want to emphasize to you guys is that like a capacitor stores charge, and that's how it is able to provide power to a circuit. An inductor stores energy, a magnetic field, and that magnetic field is what provides energy to the circuit. So as the change is maximum, the magnetic field is maximum. As the change decreases and goes to 0, then the magnetic field goes down to 0. So this is our voltage through the inductor graph. This is great because if you can understand conceptually what is happening to each of the variables in an LR circuit, then you can derive an equation. And we're going to do it both using calculus and conceptually. So let's start conceptually because that's how I taught it to you when we talked about RC circuits. First, we need to think about what's happening at the instant the switch is closed. We know that because of this inductor that opposes the current, we've got an initial current of 0. And that means that we can treat our inductor as a roadblock. But what happens after a long period of time? After we analyzed our graph, we said, well, the change in current goes down, and so the inductor no longer works. That means that the inductor can be treated as a wire. Now, I want you to think about how this is different for a capacitor. If you put a capacitor here, how would that capacitor act at the instant the switch is closed and after a long period of time? I hope you guys came to the same conclusion I did. It's actually opposite. For a capacitor, the instant the switch is closed, it acts as a wire because it doesn't have any charges on it, so it won't oppose the flow of current. But after a long period of time, when it's fully charged, it's going to have a full voltage of the battery and it's going to stop the flow of current. The voltage of the capacitor is going to be opposite the voltage of the battery, equal and opposite. So then it's going to be a roadblock for a capacitor. So that's kind of cool. They have the same properties, but it's just flipped. Okay, so in this scenario, we are going to talk about how we can use these concepts and write the equation conceptually. We know at time equals 0, the current equals 0. And we know after a very long time, the change in current becomes 0. That means that this is going to act like a wire, which means that the maximum current is going to be just the current going through a battery resistor circuit with no inductor in it. So current for a battery resistor circuit is just EMF over R. So let's use these to write an equation. We know what they look like, and we know that our exponential approach is 1 minus e to the negative t. And I'm going to put this here because we talked about it last time we talked about circuits. Negative t over tau is going to be the same in a LR circuit. And we're going to talk about what tau is for an LR circuit, but we're just going to leave it as tau for now. I don't like this bright green color. So let's start with current. When it starts at 0 and approaches, it reaches a maximum. So for current, I need to indicate what that maximum is as the multiplier in front of this expression. We already established the current is going to be EMF over R because that inductor is just going to act like a wire. So this is I. And then for voltage through the resistor, if the current is equal to, if the voltage is equal to IR, well, I do have I here. If I multiply this by R, well, this R and the R that I multiply it by is just going to cancel out. So in the end, I get EMF, which is the voltage of my battery, and then the same exponential approach equation, and over tau. Okay, for the exponential decay, we already know what the expression should generally look like. And I need to figure out what that multiplier is in front. Well, if my EMF is going to have a voltage in this direction, then at the beginning, my inductor should have a voltage that pushes current in this direction. Well, in order for the current to start off at 0, they have to be equal and opposite. And so in this scenario, my voltage through the inductor is going to be EMF E to the negative t over tau. All right, so we are going to derive the equation for current using calculus, and we've already figured out what the equation is conceptually, so we're just going to learn the calculus way to derive and make sure that it checks out with our conceptual equation. This is my loop rule. Hopefully you can see that when this switch is closed, my current is going to flow in this direction, and if I follow the flow of current, I've got an EMF from the battery, that's positive, voltage through the resistor, that's negative because it dissipates, and my inductor is going to induce a current to oppose that increase in current when the switch is closed, and that means I'm going to get a negative L di dt. Since we're solving for current, I'm going to try to get this IR, or this I, in the IR, and this DI on the same side so I can use some calculus to solve it. So I take EMF minus IR and bring my L DI dt to the right side. And this is going to seem like a strange step. And in fact, in the video, he does the same derivation, but in different steps, and still gets the same answer. So you can watch the video and decide which one you like better. This one seems kind of oddballish, but if you memorize that one step, then you don't have to worry about solving for constants. So I am going to multiply by a negative 1 over r. Weird, but it's going to make everything look nice in the end. That gives me a negative EMF over r plus I is equal to negative L over R di dt. And then I am going to try to bring all my i's together, which means I'm bringing all of my constants to the left side and then this to the right side. So I'm just going to switch them. And by doing that algebra, I end up with the reciprocal, R over LT, is equal to 1 over EMF, sorry, that should be a negative EMF over R plus I dI. And then I'm going to integrate from 0 to t and from 0 to I. Now, in this scenario, oh, I forgot this should be a dt, not a t, because I'm integrating dt, which just leaves me with t, and I end up with a negative r over lt. On the right side, I have 1 over this expression with I in it, and that gives me ln, that expression. And I'm going to write it down as I minus EMF over R because it looks prettier. And then I can include my limits from 0 to I. So now I've got my ln of, substitute I for I get I minus EMF over R, and 0 minus EMF over R, which is just negative EMF over R. And then when I want to get rid of an ln, I take e to both sides, and I'm starting to see my equation forming. This denominator, I'm going to multiply to the left side right off the bat. So I get negative EMF over R times e to the negative R over LT. And on the right side, I have I minus EMF over R. Then I add that to the other side, and I get EMF over R minus EMF over RE to the negative R over LT is equal to I. And then make it look like an exponential approach equation. I get EMF over R times 1 minus E to the negative R over LT. And that, my friends, is very similar to what we had in our previous conceptual equation derivation. Now, what we have extra here is this constant. Now, the exponent is negative t over tau. That means that if my expression r over L times t equals t over tau, then tau is equal to L over R. And this is actually in your equation sheet, so you do not need to memorize it, but you'll see the expression written out as negative t over L over R sometimes in equations. So check, this matches what we thought it would when we wrote the equation conceptually. Okay, so we have established this as our equation through calculus. We can see that our time up here is going to translate to a time constant of L over R. And just to recall from our previous unit, that time constant represents the amount of time it takes for the current to reach 63%, or if it was decaying to decrease by 63%. And yes, it is in your equation sheet, so you don't have to memorize it. To derive the other equations, we did it in the previous slide, but one thing I want you to note is that the voltage through the inductor stems from the voltage equation, and since we have an equation for current, we can plug that into this this expression and take the derivative of the current with respect to time. So that ends up giving us an exponential decay from taking the derivative of an exponential approach. Okay, we're going to throw in a few more complex LR circuits where we need to figure out conceptually what's happening, how the inductor is acting over time equals 0 or a long period of time. So switch 2 is closed, switch 1 is open. So what happens in this scenario? Well, first off, we've got a current going out of the battery when switch 1 is closed and switch 2 is open, and it's going clockwise. When switch 2 is closed and switch 1 is open, the inductor, which has a current coming down, is going to continue the current coming down, and then it's going to dissipate through the LR circuit here, because now this is the closed circuit, until it runs out of energy to power or to go through, have current going through the resistor. So in this scenario, we've got a current going through our resistor here, but it's dissipating, and so we're going to have an exponential decay equation. In this next scenario, we're going to say both switches are closed. So how is this inductor going to act? So let's say both switches are open at first and we close both of them. The battery is providing a current. How is this inductor going to act? Well, as we stated, the inductor is going to oppose the current coming into the inductor, so it's going to oppose current through this branch. And so what's going to happen? It's going to act as a roadblock, but as time goes by, it's going to, its induced current is going to get smaller and smaller and smaller as the changing current gets smaller, and then it's going to act like a wire. So at that point, we've got the battery going through through this loop and bypassing this resistor because it wants to go through the branch of no resistance. So what you're going to do now is you're going to do a bunch of conceptual questions like this involving multiple resistors and an inductor with LR circuits. So hopefully you have been taking notes and you're going to jump into that Pear Deck and complete the MCQ problems.